Okay, in this lecture, I'm going to talk about the energy stored by a capacitor. Again, I just want you guys to be able to calculate the energy stored by a capacitor. Why is this important? Well, that's what capacitors really do. When we're using a capacitor in real life, when we're designing one, we're designing a system that stores electrical energy. So what do capacitors, the ones that you can pull out of an electronics lab, do? Why would I put them in a circuit? Well, they store energy by holding charge in reservoirs. It wouldn't naturally be. I like to think about capacitors like a dam. Okay, so a dam also holds water in a place that it wouldn't naturally be, and that if there wasn't that dam there, right, that water would flow downhill. So you can store the water kind of at a high gravitational potential and then release it, and you could use that, right, decrease of potential energy to do work. Well, same thing with a capacitor. You're holding the charge in a place it wouldn't naturally be at a big potential difference. If you connect your two capacitor plates, okay, or your two different conductors, that allows the charge to move, and as it moves, that charge can do work, okay? So how much energy is stored is a really useful thing to know when you're thinking about a capacitor. Okay, so to do this, we have to go back to thinking about work. So when we're doing work to produce a charge configuration, we're essentially creating stored energy, okay? So the work done to move a charge into a potential difference is equal to the magnitude of that charge times the potential difference, okay? And the only difference between what we did here, or what we did earlier, and what we did here is before we assumed Q was coming from infinity. Okay, here it is coming from A. So essentially we're moving a charge, Q here. We're going to move it from A, and we're going to cruise over here, and we're going to put it at B. Okay, and those two things are going to be at different potentials. Okay, so that's how much work I have to do to take a charge here, Q, and move it from point A to point B. Okay, to move a bit or a chunk of charge rather than a point charge, we can describe that mathematically as saying I'm going to do a little bit of work to move a little bit of charge across some potential difference. Okay, where this delta V, this depends on how much charge has already been accumulated. So if you think about charging two capacitor plates, it's easier to move the first couple of charges because there's not a lot of charge built up on those plates than it is to move the last charge where you're really forcing, say, positive charge onto a very positively charged plate already. You got to do more work, okay, because there's going to be a stronger repulsive force, okay? So in general, you want to think if there's more charge on that plate, there's going to be more delta V, and there's going to be more work in that case. All right, so in order to calculate the total amount of work to be done, you need to integrate over all the little bits of work you did to accumulate that charge distribution. So that means you need to calculate the total amount of work that you needed to do to move a total amount of charge Q onto a capacitor. And that's going to be equal to integrating over that little bit of work. Okay, and again, as you do this integral, you can imagine the amount of work that you do, you calculate, is going to get bigger as the potential difference of the plates grow. Okay, so if I plug in here what the delta V is, which is going to be at any time, we're going to call it little q on the plates over C dq. Okay, I can pull out that constant, which is going to be 1 over the capacitance, and then I'm left with q dq for the integral. Okay, and that's an easy integral to do. I end up with 1/2 times q squared over c. Okay, and what I'm left with is the total work is going to be 1/2 q squared over c, and this is the amount of energy stored in a capacitor. Okay, so we can look at this again and think about what it means. Here we've got q squared, so that's how much charge I've accumulated on each of the 2 parts of my capacitor. One's going to be positive and one's going to be negative. Okay, so the more charge I accumulate, the more work I have to do, also the more energy that's stored. Okay, you can kind of think about that as the amount of water that's in my dam. Okay, C is this thing, this proportionality constant, but we found out for different types of capacitors, what determined C was the shape or the geometry of the capacitor itself. So again, the amount of energy is stored. It doesn't just matter about Q, the amount of charge you've accumulated. It also matters the shape of the capacitor, the geometry of it. So again, you could think of a dam situation where the amount of energy stored might also be related to the geometry of the dam itself. Okay, but this was what determines how much energy is stored by a capacitor.